Hello! Today, in the next 30 minutes or so, I will give you an overview of the largest changes in JDK 16. This will not be a deep dive into the changes. We have other sessions in the agenda that will cover them in detail. My goal is to give you a brief summary to help you decide which features you want to learn more about. My name is Aurelio Garcia-Ribeyro. I am a Senior Director of Product Management in the Java Platform Group at Oracle. I have been with the Java team since a little before the release of JDK 7. Although I will focus on the larger changes, keep in mind that JDK 16 includes hundreds of smaller changes and bug fixes that are called out in the release notes and on the updated documentation. Feel free to ask questions throughout the session using the chat function. I have a couple of colleagues that will help me answer some of them in real time. And I will leave some time at the end of the session to cover the ones that we didn't address via chat. JDK 16 is the first of two releases planned for 2021. It's the 7th release since we switched to a semi-annual release cadence, and the last release prior to the next long-term support due this September. Users of JDK 15, and for the matter for users of 12, 13, or 14, if they have not yet migrated, should move up to JDK 16. The next critical patch update, which is scheduled for April, will only include updates for JDK 16, 11, 8, and for customers JDK 7. You can also see from this slide that we offer the JDK under two different licenses. Everyone is welcome to use Openjdk 16 builds under the GPL license, and customers, developers, and those using it for personal use can get Oracle JDK 16, as well as updates for JDK 11 and 8. Customers get support on those releases so they can reach out to our team if they're running into any problems. JDK 16 delivers 17 JEPs, which stands for JDK Enhancement Proposal. That's the unit of work that we use to specify the largest changes in the platform. I've grouped them into 6 categories. We have 2 changes to the Java language. There's 2 improvements on memory management on the Java virtual machine. We have added a new API for inter-process communications and a tool that makes it easier to deliver your Java application as a standard installer for Windows, Mac, and Linux. JDK 16 also makes changes to prepare developers for future versions of the JDK. So we're trying to move them away from relying on internal APIs, and we're also paving the way for improvements in memory management that will be delivered as part of Project Valhalla. We deliver 4 features in preview or incubator so that we can gather feedback before we can add them to the platform in a more permanent way. Finally, the JEPs on JDK 16 deliver changes not only to the builds for the JDK, but also to Openjdk. And those will make it easier for developers to contribute and move the platform forward. Now let's review each one of these in more detail. But keep in mind that the JEPs represent only the most visible changes. If you dig a little deeper, you will see that every release has a larger list of changes. In this case, some of these APIs, the majority of them, are related to the enhancements that I listed in the previous page. For example, that new class is the new Unix domain socket channel. And many of the methods that are now labeled as for removal equals true are part of the effort to prepare wrapper classes for their change into value types. JDK 16 documentation calls out each one of these. Now, first, let's look at the language features. These are the changes that will be most visible to all developers. Changes to the language make it possible to write Java code more concisely, which makes it less likely to contain bugs, and since it more clearly expresses what the developer wants, it's easier to maintain in the long run. The first change is pattern matching for instance of. We saw this as a preview in JDK 14 and 15. Not being a preview anymore means that you can use these features without any special flags, and you can be confident that that will remain as they are on future versions. Pattern matching for instance of allows us to express conditional expressions of components from objects in a more concise and safer manner. Let's see an example. We've all seen or written code like this. We have an object which could hold different types, and we want to do something if it happens to be of a particular type. Now, in this simple statement, we have three things going on. First, we have to test to see if the object is a string. Then, if it is a string, we have to declare a new string variable so that we can cast the object. And after that, we have to cast the object into the variable so that we can treat it like a string. Using pattern matching, we can reduce the code into a single line that does all of those three things. The variable s is only created if the object is a string. If so, the object is automatically casted into the variable, and the variable remains in scope only inside the brackets of the if statement. If there is an else part on the conditional, the new variable is not in scope in the else part. Even with more advanced conditionals, the scope of the variable behaves as you would expect. For example, when using AND in the conditional, since the second part of the statement is only evaluated if the first part is true, S is in scope for the second part of the condition and in the brackets for that branch. If you were using OR, since the first part is only evaluated when the variable is not in scope, S will not be defined and won't be able to be used on the second part or inside the brackets. You also will get a compile time error if you create an expression that always evaluates to true or to false. For example, if you were to ask if an expression is of type object, which would always be true. That's an error that you would get if you try to use S in the latter part of the statement. The second change to the language in JDK 16 is the addition of record types, which also were delivered as a preview first on JDK 14. Records save developers the need to deal with some of the boilerplate that you have to create to write a class that simply aggregates immutable data. Take, for example, a simple class that expresses a coordinate. We only want to pass around an immutable pair of integers, x and y. However, we're going to need a constructor to set those values. We also want all classes to implement an equals. And of course, let's not forget about the hash code. We also need to see the values. So if you write a toString, you don't just want to get the name of the class, you want to get the values. And we want to be able to access those values. So we need some methods to read them. Note that the accessors are not using the traditional getX and getY, but just the name of the fields. Now, all of this extra code could be auto-generated for you by your IDE. So writing it may not be a big deal, but that won't help us when we're trying to read the code and understand what this class is for. We will still have to review all of this auto-generated code before we can be sure that this is a plain class, that there's nothing but ceremony behind those methods. Now, what if we could let Java handle all of these for us? Instead of saying class, we say record. And there. The compiler can make sure that our record type gets all of those required methods without us having to include them. If for some reason some of those methods was not just boilerplate, let's say you need a constructor so that you can do validation on the incoming data, well, you just implement the constructor and the compiler provides all of the other ones. This way, whatever is written is indeed required, and when reading the code, you only see things that are necessary, no boilerplates. In some future JDK release, we plan to make it so that you can use pattern matching also on records. Now, while the changes to the language make it easier to write new code, changes to the Java virtual machine are improvements that everyone can take advantage of, even if all you're going to do is run code compiled on older versions on this new release. The engine that runs your Java program has improved, and therefore all programs get better performance and they just work better, even if you don't change anything. JDK 16 brings us two changes to the JVM. For those using the set garbage collection, which is not the default, but has been available in experimental mode since JDK 11 and in non-experimental mode since JDK 15, JDK 16 delivers an improvement on how garbage collection is processed. In order to truly parallelize the way the garbage collection phase, the thread stack processing has been moved from save point to the concurrent phase. Now, this removes the last important roadblock for making CGC take advantage of parallel processing and was a requirement for the CGC goal of sub-millisecond time in save points. The second JVM enhancement is on the area of memory management for metaspace. Since metaspace was introduced with JDK 8, it has been notorious for its large off-heap memory usage. Now, this is not a problem for most applications, but in some cases it could result in excessive memory wastage. Before this change, when the memory on metaspace was no longer needed, it was returned to the JVM, but the JVM did not in turn return it to the operating system. With this change, we can now allocate memory in smaller chunks, reduce the cloud loader overhead and fragmentation, and makes it easier to return unused space to the operating system. Now, changes to the libraries can either bring new functionality or sometimes improve on the existing functionality. With JDK 16, we got one of the first case, an enhancement to the APIs. We also get a new tool to make it easier to deliver Java applications. So, JDK 16 introduces Unix domain socket channels. They're very similar to TCP/IP sockets, but are meant to be used for inter-process communication rather than for communicating with other servers. As such, they can be addressed by file system path names rather than Internet Protocol ports and numbers. They're more secure and efficient than using the equivalent TCP/IP loopback connections. Unix domain sockets are used by all major Unix platforms and by Windows. This JEP will add support for the features that are common across Unix and Windows. Until a few years ago, the recommended way to use Java on a system was to have a single shared Java runtime and have all Java programs run on it. This was meant to save you precious hard drive and allows you to download Java programs by downloading only the bytecode, not a full copy of the runtime, saving you bandwidth. Unfortunately, this means that Java applications delivered as jars behave differently. You first have to install the Java runtime and then distribute the jar and somehow pass the jar to the runtime. Windows users will not find those Java programs in the start menu. It won't be listed in the add remove programs. And more importantly, this means you cannot distribute them using standard tools that require standard packaging format like RPMs for Linux or MSI for Windows. Nowadays, it's more common to have applications isolated without shared components. This is particularly true if you're using containerized systems on which each application no longer shares anything with any other. Also, storage and bandwidth have increased significantly, so moving around 300 to 500 megabytes for an update is no longer a deal breaker for most systems. Using this new packaging tool, you can create an installer that will wrap your application plus the runtime, or you can even use a smaller version of the runtime if you choose to use JLink, into something that looks and behaves like a native installer for each platform. So you can do an MSI installer for Windows, or a DMG for Mac OS, or an RPM or Debian package for Linux. Now, moving the platform forward is not only about adding new features. It's also about making sure that the programs behave correctly and are not inadvertently doing anything that will make it harder to uptake future versions. JDK 16 delivers two changes that make it less likely that you will have problems to uptake later releases of Java. The first one, perhaps the most scary change in JDK 16 is that we're going to strongly encapsulate JDK internals by default. One of the contracts between the maintainers of the Java platform and the developers is that there is a set of APIs that developers are welcome to use and which future versions of the JDK are likely to continue having. In order to deliver those APIs, the maintainers of the Java platform use internal APIs, which are meant to be used only within the platform. They're not meant to be part of the implied contract with the developers. These internal APIs are subject to change without notice, so any program that relies on them might break when applying any update, even a minor update, or a point update. Until JDK 9, these internal APIs were not documented. But since developers have access to the source code of the JDK, they're quite easy to find. And once found, they can be called like any other API. Now, there are warnings when compiling if you use those APIs directly. And we have warnings not to use them at least since 1996. But still, there's some developers that rely on them. And even if you're not using them directly, there were many common tools and frameworks that used them for many years. So the result was that when JDK 9 came out, most, if not all, non-trivial applications relied on them. With JDK 9 and the introduction of Jigsaw, we now have the ability to enforce that only JDK internal code should access those internal APIs. But if we had turned that on by default on JDK 9, it would have made it so that many of those libraries and frameworks would have stopped working with little notice. Instead, we chose to just add more explicit warnings on JDK 9 so that when programs access the internal APIs, we would say, you should not be doing this. And we said, in a prudent amount of time, we will start enforcing the encapsulation. Now, that was 3.5 years ago, so we could say that a prudent amount of time has passed. And we're now enabling stronger encapsulation by default. With JDK 16, this means they're still accessible. Before JDK 16, it was still accessible, but with a warning. Now it's no longer accessible. This change applies to most internal APIs, but there are a few notable exceptions like Sun, Misc, and Safe, which are still widely used and for which there is no good replacement. Now, most internal APIs were being used just for convenience. So those you should be moving to a different alternative. Now, if you're still running programs that use internal APIs, it will be possible to pass a single command line option that will make JDK 16 behave as JDK 15 and earlier did. That is, warn you rather than blocking. In some later release, we will remove that single command line option and will require a different command line for each internal package. Okay, we have a tool called JEPs that will help you identify any instances of internal usage of internal APIs, even if you don't have the source code for them. Another change is that we are now giving you warnings if you use value-based classes in a way that will not work in the future. So as part of Project Valhalla, we're working on a new type of class for Java called primitive classes. And those will be used on instances that will be identity-free and capable of inline or flattened representation. Now, some of the classes that currently exist in Java are likely to be converted to these primitive classes. Those classes are currently called value-based classes in the API specification. The primitive wrapper classes, such as JavaLang Integer or JavaLang Double, satisfy most of the requirements to be designated value-based, except that they still expose public constructors that have been deprecated since JDK 9. With this JEP, we're going to tag them not just as deprecated, but include the for removal equals true tag to those constructors. We also will add the JDK now will emit warnings if you try to synchronize on instances of any value-based class, right? You always get runtime warnings, and additionally, when possible, you will also get compile time warnings. Another category is the preview and Incubator features. The shorter period between 6 months allows us the opportunity to preview features before baking them into the standard. JDK 16 will let you try out and provide feedback on 4 such features. The thing to understand is preview and incubators, they serve a similar function. They allow us to gather real-world feedback on a planned feature while signaling that it should not yet be considered finalized. Incubators are used for tools and libraries, since those can easily be constrained within the module system. Preview is used for language and VM features, which cannot be neatly contained within a module. In either case, using these features requires additional work, both at compile time and at runtime. Developers need to pass on a flag to the compiler if they want to compile code that uses preview features. And at runtime, you need to pass a flag in the command line to enable them. Preview features are fully specified, they're fully implemented, but they're not yet permanent. So you should not assume that they will work as they do now in any future JDK version. Okay? And the purpose of the flags is that we don't want to have anybody using them unknowingly. We don't want somebody to write a library that uses preview features, perhaps compile it using the correct flags, but then pass the compile code to other developers and let them build programs with that library, unless those developers are aware that the library is using preview features. Now, this is a common question, so how many times do you have to be in preview before you get added into the standard? There is no set number of previews or incubators. Some simpler features, or those that are better understood, are just added without being a preview. Others might need 1 or more previews. So far, most language features have had 2 previews before being added to the standard, and the APIs have remained in incubator mode for up to 3 releases, but there's no set rule. Okay, so with that in mind, here are the preview features for or incubators for 16. Sealed classes. They restrict which other classes or interfaces may extend or implement them. Okay, so a class hierarchy enables the reuse of code via inheritance. However, the purpose of a class hierarchy is not always to reuse code. Sometimes it's just to model the various possibilities that exist in a domain. Okay? When you're using it this way, Java developers provide you very limited options before JDK 16, or rather before sealed classes. You can either make a class final, so it has 0 subclasses, or you can make the class or its constructor package private, so it can only have subclasses in the same package. However, if you do that, the user cannot access the key abstraction, the superclass. So you cannot allow access to the superclass without also allowing them to extend. What we really want was a superclass to be widely accessible, but not widely extensible. So sealed classes. Let's take a simple example. A class is sealed by applying the sealed modifier to its declaration. Then, after any extends and implements clauses, you add the permits clause and specify which classes are permitted to extend the sealed class. A sealed class imposes 3 constraints on the permitted subclasses. The sealed class and the permitted subclasses must belong to the same module, and if you're using an unnamed module, in the same package. Every permitted subclass must directly extend the sealed class, and every permitted subclass must choose a modifier to describe how it continues the sealing initiated by the superclass. It could be final and allow no more subclassing. It could in turn be sealed, which means it will have its own set of permitted subclasses. In this example, we'll make those final. Or it could be non-sealed. A sealed class cannot prevent its permitted subclasses from doing this. One and only one of these modifiers, final, sealed, or non-sealed, must be used by each permitted subclass. JavaLang Class will get 2 new methods, so that code using reflection will be able to determine if a class or interface is sealed, and if so, get a list of the permitted subclasses. And the other new API with JDK 16 is a vector API that will give developers a way of expressing computations that will reliably translate at runtime to vector hardware instructions on supported CPUs. Vector operations enable more work to be performed in a single CPU cycle, so this can lead to significant performance gains. Although Hotspot supports auto-vectorization, the set of transformable scalar operations is limited, and changes to the code shape could lead to Hotspot missing potential optimizations. The Vector API will let developers solve this by giving them the tools needed to directly express vector operations. Now, most developers will not have to do this directly. We expect that library developers will take advantage of this API to optimize the common libraries that most developers rely on. Once that happens, most developers will get that significant performance improvement merely by updating to versions of those libraries and running on newer JDK versions. Here's a conceptual example. If the same operation will be executed on a group of values, it might be possible to load those values into vectors and execute the operation on the complete set. In this example, rather than needing 4 multiplications, 4 additions, and 4 assignments, we can get to the same result using CMD instructions for 1 multiplication, 1 addition, and 1 assignment. We also get to test 2 APIs courtesy of Project Panama that will make it simpler to run non-Java code, specifically now C libraries, for x64 and ARM64 platforms. Although Java has supported native method calls using Java Native Interface, or JNI, since Java 1.1, this has always been brittle and hard. Using JNI requires developing and maintaining multiple artifacts like a Java API, a C header file, and a C implementation. And you have to do this for each supported platform, since the result is platform dependent. And it requires different tool chains in each platform. There's other frameworks that have appeared over the years that improved on this, but it's still less than ideal. Project Panama aims at making it trivial for Java developers to use any native library. These 2 APIs provide the foundation for Java programs to interact with native libraries. The Foreign Memory Access API in particular is meant to provide a secure mechanism for accessing memory outside of the Java heap. Many programs currently accomplish this by using sun, misc, and safe, which, as the name implies, is not a safe practice. Once the APIs are finalized, we should be able to further reduce the need of keeping sun, misc, and safe available for these operations. Finally, not all of the work in the JDK itself shows up directly in the binaries that we release. JEPs are also used to deliver improvements to the Openjdk project. Now, these changes are only directly visible to developers working on the JDK code itself. The rest of developers and system administrators, those that just use Java to write or run Java programs, will get the benefit of these changes indirectly, since they will make it easier to get work done, and it's therefore more likely that we will get improvements faster. Let's take a look at these ones. Hotspot, the Java virtual machine in Openjdk, is written mostly in C++. Up to JDK 15, the language features used by C++ code in the JDK were limited to the 19-03 language standards. This JEP formally allows the use of C++ 14 language features. I added in the JDK source code comment to the name of the JEP, because the first time I saw it, I thought, what? Enable C++ language features in Java? It's only for those writing code in Hotspot. We also migrated the source code from Openjdk. The source code used to be maintained in Mercurial for source control. It has now been migrated to Git, which uses significantly less metadata, about a quarter of the size, and which has much better tooling. Now, it was not just the source code that was migrated. Some of the existing tools were updated to make sure that they continue to work and provide value now that we're running on Git. The question of which provider to choose after the Git migration, whether to use self-hosting or to rely on an external provider, was addressed by a second JEP. The result of that was that GitHub was selected as the repository for the source code of Openjdk. This is the result from Project Scara. The final two JEPs are about integrating two ports, Alpine Linux and Windows on ARM, to the JDK mainland repository. The Alpine Linux distribution is widely adopted in cloud deployments, microservices, and container environments due to its very small image size. A Docker-based image for Alpine Linux, for example, is less than 6 megabytes. Enabling Java to run out of the box in such settings will allow Tomcat, Jetty, Springs, and other popular frameworks to work in such environments natively. And as most of you may know, Windows is now available on consumer and server class ARM systems. Okay? Although Oracle is not yet making builds of these ports available outside of the early access builds of future JDK on Alpine Linux, the integration of these two ports into the mainline will make it easier for us to do so in the future. That's it for the JEPs in JDK 16. Now let's see all the details about the release. This is the list of certified configurations for JDK 16. It's almost the same as the platforms on which we certified JDK 15. The only difference are that we have bumped up the minimum update of Oracle Linux and Red Hat Linux required if you're running on ARM64. It used to be 7.6. Now we've bumped that up to 7.9. And we have added support for Ubuntu Linux 20.10, which released between JDK 15 and JDK 16. So there's really no surprises on the certified configuration matrix on this release. Now, where should you find JDK 16? We offer JDK 16 under two different licenses. You can get a supported version of JDK 16 under the JavaIC OTA license, which can be used for development, for personal use, and for Oracle customers, including JavaIC subscribers and anyone running in the Oracle Cloud, by visiting oracle.com Java download. You can also get Openjdk binaries for JDK 16, which they have the exact, they're the same binary. The difference is the license. Well, mostly the license. There are some other minor changes, like if you write a Java minus version, one will say JDK and the other one will say Java. You can get the Openjdk binaries for 16 and their GPL from jdk.java.net/16. I've given you a quite brief overview. If you want to learn more about any of these features, the first thing to do would be to look at the catalog for the sessions. There are deeper dives into several of these JEPs later in the day. You can also go directly to the main source and visit openjdk.java.net. Each one of these JEPs has a detailed description from which most of the text in this presentation was borrowed, but they offer a lot more detail and examples. Each JEP will also point you to the relevant discussion list, which has even more details, not only on the feature itself, but also on the discussions that led to it. If you would like to weigh in, especially about preview features and APIs and tools in the Incubator modules, this would be a great place to start. Okay, they're really easy to read. With that, let's see if there's some questions that have not been addressed already via chat. We have a few more minutes. Let's see. Okay. With JDK 17, the next LTS release being just 6 months away, why should I update JDK 16? Why not just wait for JDK 17? Well, there's always a new release coming out 6 months from now. If you're a developer, you probably don't want to miss out on some of the improvements that have been delivered on JDK 16. But even if you have no intention of deploying on JDK 16 and you plan to deploy only on JDK 17, it would still be a good idea to try to run your code, and if you have it available, compile it on JDK 16. That way, the changes that you're seeing now, if you have to correct anything, you'll be much closer to being ready for JDK 17, and you won't have to start your migration process then. I guess you could also, by the way, try the JDK 16 early access builds, which are available. But developers, you probably don't want to skip any release. They're just too good. If you're deploying and using it in production, I expect you will not be the only one that goes from 11 to 17. Next question. When will Oracle block access to all internal APIs for good? That's in reference to the encapsulation of internal APIs that we're making it stronger. We have no intentions of, at some point, locking it down in such a way that you cannot break encapsulation. What will happen in some future release is that instead of one convenient command line option that it's just revert to allowing me to use all of the internal APIs, you will have to add one different command for each one of the packages that you want to expose. Having said that, it's a really bad idea to take advantage of the flag that will enable you to access internal APIs. Even though the internal APIs can still be accessed, we're serious about the fact that they can be removed or changed in any release. We've been very careful not to do so before JDK 9 because people were using them quite a lot. Now, after JDK 9, the number of people using those internal APIs has decreased significantly to the point that we now feel comfortable blocking them by default and asking you to pass a command line if you want to revert. Once we see that those internal APIs are no longer widely used, we will feel a lot more comfortable about changing them. So even though you can revert back, it's really not a good idea. So please stop using those internal APIs other than the critical ones that are not affected. So SandMist can save some of the reflection ones. Those are there's still no other mechanism for getting there. We will provide mechanisms that will allow us to at some point remove those as well, but that is far in the future, and you will get several releases warning like you got between the 9 release and JDK 16. Now, somebody's asking, some of those memory improvements, they're only on CGC. Should I be using CGC instead of the default garbage collector? Well, I'm a big believer of if it's not broken, you don't need to fix it. CGC is not the default because we think that for many use cases, it doesn't have to be the default. So if you're not experiencing problems with your memory garbage collection, feel free to try it out, but I wouldn't recommend that you just adopt CGC because it's the latest. On the other hand, if you do want to have much shorter pause times, it's worth looking into CGC and trying that out. So if you're one of those applications that needs much shorter delays for pause for garbage collection, try it out. I think you will be pleasantly surprised. When is the Mac Arch64 or ARM64 port coming? I believe we plan to have it with JDK 17. So the port that's the Oracle binaries for Arch64, I think will be available for JDK 17. I'm not sure if they're yet in early access or if they're coming pretty soon. I'd have to check, but yeah. And when is the Alpine Linux port coming? So we have been providing early access of the JDK on Alpine Linux for several releases now. And we will continue to provide it only in early access until we get enough feedback from you guys, from our users, asking for it. So if you would like to use Alpine Linux and you need to have it officially supported and not just in early access, reach out to us. You have my contact information, and let us know. And the more people tell us that, the more likely it is that we will add support for Alpine Linux in a release not too far in the future.